section, guess what? We're going to look at two more ways that we can tell if a series converges or diverges. And the first one of those is called the ratio test. In the ratio test, we have this series, and we're going to assume that terms are not zero in this series. And we're going to construct a ratio between a term and the term that comes after it. So in this series, if I have n plus 1 divided by a to the n, and I take the absolute value of that, and then I take the limit as n goes to infinity of that absolute value. If this is less than 1, then the series converges absolutely. If the series is, or the ratio is greater than 1, or it's infinity, then the series diverges. And if this ratio is equal to 1, the test is inconclusive. It doesn't tell us anything. Okay, so that's the ratio test. I've got to have non-zero terms, and then I construct a ratio between the term and the term that comes after it. Let's look at some examples. Here's a series we'll want to know about. Two to the n power over n factorial. So we're going to take the limit as n goes to infinity, and now we're going to make a ratio here and take its absolute value. So I've got 2 to the n plus 1 over n plus 1 factorial, all of that over 2 to the n over n factorial. Okay, we can kind of sort this out a little bit. And write 2 to the n plus 1 times n factorial over 2 to the n times n plus 1 factorial. Okay, and working that out, I get the limit as n goes to infinity of 2 over n plus 1. Okay, and this is how that works. This is one higher power of 2 than this, so that's where the 2 comes from. N plus 1 factorial is just n plus 1 times n factorial. So the n factorials will cancel out, and I'm left with n plus 1. And as n goes to infinity, this limit is going to go to 0. And we know 0 is less than 1, which means that the series converges. And let's start with our series. This time n equals 0 to infinity, n squared times 2 to the n plus 1 over 3 to the n. So we're going to write this as the limit as n goes to infinity of n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1. And then we need to divide that by the same thing with n. But instead of dividing, I'm going to flip this over and multiply, which gives me 3 to the n over n squared times 2 to the n plus 1. Okay, when I work that all out, cancel out things that can be canceled, I get the limit as n goes to infinity of 2 times n plus 1 squared over 3 n squared. Okay, I have equal powers of n here. So as n goes to infinity, they kind of cancel out, and I'm left with 2/3 for my limit. This is also less than 1. So on this series, I can say that it converges. Let's look at another one. N to the n power over n factorial. Okay, when I write my limit, I'm going to have n plus 1 to the n plus 1 power divided by n plus 1 factorial, and then I'll flip that over and multiply. So I'm going to have n factorial over n to the n power. Okay, I know my n factorial is going to cancel out with n plus 1 and leave me with just the n plus 1 there. And then my n plus 1 to the n plus 1 power divided by n plus 1 is going to reduce the power by 1. So I'm going to have just n plus 1 to the n over n to the n. So this gives me the limit as n goes to infinity of 1 plus 1 over n to the n power, and that's equal to e, which is greater than 1. And greater than 1 means that this series diverges. Okay, we've seen a couple of examples that converged and also an example that diverged. Let's look at an example where this test is not going to help us out. This time my series is -1 to the n power times the square root of n over n plus 1. So if I take the absolute value take the limit of the absolute value. Okay, absolute value means I don't have to include this part. I'm going to have square root of n plus 1 over n plus 2 times n plus 1 over square root of n. And that gives me the limit of the square root of n plus 1 over n, put both of the square roots together, times n plus 1 over n plus 2 do this. And as n goes to infinity, n plus 1 over n is going to go to 1. So I'm going to have the square root of 1. And here I'm going to have infinity plus 1 divided by infinity plus 2, which is essentially 1. So the limit equals 1, which means it is inconclusive. Okay, this test did not help us for this particular series. Okay, we have another test that we could try called the root test. This is theorem 9.18 on page 634. And the format is very similar to the ratio test that we just looked at. If I have a series a sub n it converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. Okay? This is very familiar, very similar to what we just did with the ratio test. This part is different, but the result is the same. If it's less than 1, it converges absolutely. If this limit is greater than 1, or it's infinite, then the series diverges. Just like it did with the ratio test. If the limit is greater than 1 or it's infinite, it diverges. And you've probably already guessed this, but if this limit is equal to 1, the test is inconclusive. Okay, so again, the format, very, very similar to what we just did with the ratio test. Let's look at some examples. So here's our series, and we're going to apply the root test to this series. We're going to write the limit as n goes to infinity of the nth root of our series. So rewriting this with fractional exponents, we're going to have e to the 2n over n divided by n to the n over n. Of course, the n over n cancels out. The n's up here also cancel out. And so I get the limit as n goes to infinity of e squared over n. Well, e squared is a constant. When n goes to infinity, this fraction goes to 0. So when it's 0, that's clearly less than 1. We say that it absolutely converges. Okay, and if you're not so sure about the usefulness of this test, try using this same series and doing the ratio test with it. Wow. In this chapter, you've learned 10 different ways to determine whether a series converges or diverges. Okay, we're going to work a few examples in a minute, but I want to point out a couple of things. First of all, there's a table on page 636 that goes through all 10 of the tests, how to set them up, what they mean. I would strongly encourage you to add that to your notes so you can refer to it quickly. Okay, in general, when we're trying to decide if a series converges or not, these are the steps you should take. Step number 1. Check and see if the nth term approaches 0. If not, that nth term doesn't approach 0, the series diverges. Number 2, is my series a special type? Okay, we've looked at geometric, P-series, telescoping, and alternating. All of those are special types of series that have their own rules for converging and diverging. Okay, if I don't have a special type, can I use the integral test, the ratio test, or the root test? Okay, and if none of that works, this is kind of my last resort. Can I compare favorably to a special type? So basically, can I kind of simplify my series until it looks like one of these special types, and then know from what the special type does, what's my series going to do? Okay, so we've got several examples that we're going to work through. So here's the first one. N plus 1 over 3n plus 1. Okay, as n goes to infinity, this is not going to go to 0. So terms do not go to 0, so it must diverge. So that one wasn't too hard. Okay, so this is a geometric series, and the ratio is pi over 6, which is, of course, less than 1. So this one converges. Okay, the third one here. Okay, in this one we're going to look at the function f of x that's equal to x times e to the negative x squared. And this is pretty easy to integrate. So we're going to use the integral test. Which tells us that this series converges. Okay, 3 down, 4 to go. This one looks a lot like the first one where I had n plus 1 in the numerator. Same denominator. Okay, but the nth term in this series could be compared to the nth term in the harmonic series. Okay, after using the limit comparison test, we can see that this series diverges. Okay, that negative 1 to the n power tells me that this is an alternating series. Okay, and the nth term is going to approach 0 since I've got the n in the denominator. And so I'm going to check, does a to the n plus 1, is that less than a to the n? When I look at this, yeah, when I increase this by 1, the denominator gets bigger, which means that the term gets smaller. Okay, so I can use this alternating series test and see that this converges. Okay, for our next series, okay, since I've got a factorial in here, the ratio test might be a good choice because when I take ratios with factorials, they tend to kind of all fall out. So when I see the factorial, that should make me think, let's try the ratio test. Okay, and when I do apply the ratio test, I see that this series diverges. Okay, last one. Okay, in this series, I have this power of n. And this suggests to me that maybe the root test is going to be a good choice. Because what do I do in the root test? I take the nth root of something. So if I have a power of n, taking the nth root gets rid of that. Okay, and the root test tells us that this series converges. Okay, like I said a minute ago, we found 10 different tests that help us to determine if a series is going to converge or diverge. You got the 4-step process that you can go through to figure out which test to use. And again, look at the table at the end of this section. Make sure that you've got that somewhere handy to help you go through all the different tests.